Imagine a robot designed to water your garden, ensuring each plant gets the perfect amount of hydration. It does a fantastic job during the summer months, keeping your garden lush and vibrant. The robot knows exactly how much water each plant needs to thrive, thanks to its advanced sensors. But then, autumn arrives. Temperatures drop and rainfall increases, changing the garden's needs. Your plants now need less frequent watering due to the cooler, wetter conditions. However, the robot, stuck in its summer routine, continues to water as before, not adjusting to the new season. This leads to overwatering, which can harm your plants by drowning their roots. This simple example illustrates a key challenge in artificial intelligence and machine learning. AI models are often trained on a fixed data set, which may not account for future changes. This data set represents a specific point in time or a limited set of conditions, making it static. When the real world changes, these models struggle to adapt to new conditions. They cling to outdated information, unable to update themselves. This leads to inaccurate or ineffective results, highlighting the need for adaptive AI systems. In the following chapters, we'll explore how continual learning can address these challenges and pave the way for truly adaptive AI. One proposed solution is to retrain the robot gardener from scratch every season. This would involve feeding it entirely new data on autumn plant care, ensuring it understands the specific needs of plants during this season. However, this approach presents several significant problems. Firstly, retraining from scratch is incredibly data-intensive. It requires collecting and labeling vast amounts of new information for each season, which is a monumental task. This process is not only time-consuming, but also extremely expensive. Secondly, it disregards all the valuable knowledge the robot acquired during the summer. The robot essentially forgets everything it learned about general gardening principles, which is a significant loss. Finally, constantly retraining AI models leads to a high computational cost, consuming vast amounts of energy. This is both financially and environmentally unsustainable, contributing to higher operational costs and increased carbon footprint. Imagine having to retrain a complex AI system used in healthcare or finance every time there is a slight shift in market trends or patient demographics. The inefficiency would be staggering. This seasonal challenge highlights the need for a more adaptive and efficient solution. Continual learning addresses the inefficiencies of traditional AI models. This method enables AI models to learn and adapt continuously from new data, overcoming previous limitations. Imagine a robot gardener that learns from its mistakes and adjusts its watering schedule as the seasons change. Instead of discarding past knowledge, continual learning builds upon it, enhancing efficiency. This allows AI models to become more knowledgeable and versatile over time. They can handle new situations and challenges without needing a complete reset. This adaptive capability is crucial for developing AI systems that can operate effectively in dynamic, real-world environments. To address the need for adaptation discussed earlier, let's explore a spectrum of approaches for continual learning. Continual learning is not a single technique, but rather a family of approaches, each with its own unique strategies and methodologies. These approaches address the challenge of learning from continuous data streams in different ways, ensuring that AI systems can adapt and evolve over time. Some common methods include regularization. These techniques aim to prevent the AI model from forgetting previously learned information, a phenomenon known as catastrophic forgetting. They do this by imposing constraints during the learning process, ensuring that new information does not overwrite the old. Replay. This method involves storing a small subset of past data and replaying it to the model periodically. This helps to refresh its memory of previous experiences, allowing the model to retain important information over long periods. Optimization. These approaches focus on optimizing the learning process itself, making it more efficient and effective. This ensures that new knowledge is integrated effectively without disrupting previous learning, maintaining a balance between old and new information. Representation and architecture. Some methods focus on designing AI models with specific architectures or data representations that are inherently capable of continual learning. These designs inherently support the ability to learn and adapt over time. making the AI more robust and versatile in dynamic environments. Evaluating continual learning, measuring progress and challenges. Evaluating continual learning models presents unique challenges, as discussed in Chapter 4. Unlike traditional AI models trained on a static dataset, continual learning models are constantly evolving. This makes it difficult to assess their performance at a single point in time. Researchers are developing specific metrics and benchmarks to evaluate continual learning models, building on the adaptive strategies we explored earlier. These metrics consider factors such as the model's accuracy on new tasks, its ability to retain previously learned information, and its efficiency in adapting to new data, aligning with the overall theme of adaptive AI.